is titled Combining Functions. We're going to add, subtract, multiply, and divide two functions. Then we have to talk about the composition. Of two functions. Okay, so just a real quick review. If I asked you to do f plus g of x, given two functions f of x and g of x, f plus g of x just means f of x plus g of x, right? And f minus g of x is equal to f of x minus g of x. F times g of x is equal to f of x times g of x. And this one in particular, I don't know why. I think it's partly because of the notation maybe, but number 3 I see a lot of mistakes on. Students read this one on the left, f times g, they multiply the functions, and then they read this as needing to multiply another x into that. And that's not what this means. F times g of x means x is the variable in the equation. You're just multiplying two functions together. F times g, and the variable just happens to be x. It's f of x times g of x. It doesn't need another x multiplied to it. Am I making sense? Okay. The fourth one, f divided by g of x is equal to f of x divided by g of x. But you got to remember on these to state g of x cannot equal 0. You can't divide by 0, so the function g cannot equal 0. So example 1, f of x equals 3 over x minus 2, g of x equals negative 1 over x plus 3. So let's talk about f plus g of x. It's the same of f of x plus g of x. So f of x is 3 over x minus 2. We're going to add that to the g function, which is negative 1, over x plus 3. Now you really got to remember, we talked a little bit about this at the beginning of the year this year. We practiced a few of these types of problems. How do you add these together? We have to have a common denominator, yeah. So this has an x minus 2. This expression on the left has an x minus 2. This one does not have an x minus 2. So what must it have? It must have an x minus 2 in the numerator and the denominator. This side now must have an x plus 3. So this expression on the left becomes 3x plus 9 in the numerator, all over your common denominator of x plus 3 over x minus 2. Be careful on the right side that you distribute the negative 1. This becomes negative x plus 2 all over your common denominator, x plus 3 all over x minus 2. When you add these two together, now that they have a common denominator, that denominator doesn't change. When you add fractions with the same denominator, you get a fraction of the same denominator. So x plus 3 times x minus 2. And in the numerator, you combine like terms now to get 2x plus 11. So we just added two functions. What would the only difference have been if I changed this to a minus sign? Would you have done something the exact same way? I mean, almost the exact same way. You just subtract these like terms over here instead of adding, but the method is the same. You still have to get a common denominator, right? We're not quite done with this one, though. Isn't this in the form of a fraction? What does that mean? There are some problems now, then. If you don't state this next part, you do not get full credit on the test. Okay? In addition to the answer here, you must include with the answer x cannot equal negative 3. What else can x not equal? 2. Okay, let me repeat that. If you do not include that as part of your answers, you can't get full credit. Because you can't divide by 0. A value of negative 3 would cause you to divide by 0. Same as a value of 2, it would cause you to divide by 0. That's no good. Let's do part B. Multiply. F times g of x. This is 3 over x minus 2 times negative 1 over x plus 3. The nice thing about multiplication, what is the nice thing about multiplication? A fraction specifically. You do not have to have, you don't have to have a common denominator. You just multiply straight across. Doesn't matter what the denominators are. It doesn't even matter if you have like terms. You just multiply straight across. We're going to have 3 times negative 1, which is negative 3. And I would recommend that you just consider these in parentheses for right now and just write x minus 2 times x plus 3. I would not recommend that you multiply these two together because it's harder to tell what the domain restrictions are. If it's in factored form, it's easy to glance at that and say, okay, x can't equal this, x can't equal that. If you multiply them together, you're just going to have to factor it back out again to find the domain. So what do we include as part of the answer? X is not equal to 2. X is not equal to negative 3. There we go. Yep, you can leave it like that. That's perfectly fine. Part C, are you recalling a lot of this from last year, a lot of this stuff? Okay. F divided by G, this one's a little trickier. I would actually recommend that you write it this way. 3 over x minus 2 divided by negative 1 over x plus 3. And instead of writing it as a fraction divided by another fraction, that's called a complex fraction. It seems to get a little messier that way. How do you divide two fractions? The reciprocal of which one? Yep. You multiply it by the reciprocal of this. So this problem turns into 3 over x minus 2 times x plus 3 over negative 1. And if we multiply those two together, that becomes 3 times x plus 3. Again, I'm leaving it in factored form to better see what the domain is going to be. Negative 1 times x minus 2. Now, if you're not listening carefully here, you're going to miss something very important. So please listen carefully. What is the domain? So x cannot equal 2 right here in the denominator. Is that the only one? If we just looked at this alone and didn't consider the rest of the problem, if we just looked at this, what would you say the domain restriction is? X cannot be 2. But where did this answer come from? Didn't it come from this over here? In order for this to be possible, didn't we have to first divide these two functions? In order for this to be defined, there were actually two values that x could not equal. Even though it doesn't show up in the answer, it shows up in the original problem. Here x can't equal 2, but what can x equal here? -3. Now, you guys listening carefully? I know it doesn't show that in the answer, but in order for us to get this answer, didn't this have to be defined? And it's not defined when x equals -3. So that's also part of your domain restriction. You have to consider every step that you do in the problem. In order for it to be defined, you have to state those domain restrictions, even at the very beginning step of the problem. Okay. Your test question is almost identical to this one. You have two functions. Okay. I ask you to add, subtract, multiply. Okay. Yeah. We had a question back here. Yeah, there is. If you were to write this the other way, in order to clear this fraction from the bottom of this whole entire, this is kind of confusing when you have a fraction inside of a fraction, but in order to simplify this, okay, you multiply this by the reciprocal, right? If you multiply a fraction by the reciprocal, doesn't it cancel it out? But if you do something to the bottom of a fraction, you also have to do it to the top of the fraction. And that's why you multiply always by the reciprocal of the second one. Does that make sense? Okay, let's go on. I know there wasn't a ton of practice with adding, subtracting, multiply, divide, but you guys feel okay about it? Let's go to composition. The composition of two functions, this is also something that we did quite a bit of in Algebra 2 last year. It looks like this: given f of x and g of x, two functions. This operation right here, f with an open circle, remember that? F with an open circle means this: f of g of x. That's how you would read that out loud, f of g of x. So instead of taking two functions and adding them by combining their like terms, we take one function, place it completely inside of another function. So the g function becomes an input. Okay. Now just a real quick discussion on the domain. Okay. Domain restrictions. Whatever doesn't work for g also has to be excluded in the composition f of g of x, because if it doesn't work in g, we can't use it as an input in f. And I'll talk more about that when we actually do an example here, but just a quick refresher, then we'll do a more complicated problem. If f of x is equal to x squared plus 2, g of x is equal to x plus 1, I ask you to find f of g of x for part A. F of g of x. What that means is this kind of notation. More students prefer this second notation to the first one for some reason. F of g of x. What is g of x? X plus 1. So this f of g of x could be thought of as this, f of x plus 1. Instead of saying f of g of x, just replace g of x with its actual function, x plus 1. Now we have to consider what the f function is saying. This is the f function right here. What it's saying is you take some input, because all x is an input. You take an input, you square that input, and you add 2. I would always recommend you make your x into an empty parenthesis. Now that input becomes squared, and then you add 2 to that. What goes inside the parenthesis? X plus 1. Please resist the urge to just distribute x, but that doesn't work. Okay? I think we talked about that early on this year. X plus 1 squared means x plus 1 times itself. X plus 1 times x plus 1. You're going to end up with x squared plus 2x plus 1. And then you add 2 to that. So you get x squared plus 2x plus 3. Let me ask you something slightly different. And pay attention to the difference here. Part B, what if I asked you to do f of g, but instead of at x, I want you to evaluate the composition at an actual value. So something like f of g of 2. Yeah. Yes, you are right. If you think about this using the other notation, f of g of 2 can be written this way, f of g of 2. You always want to start these problems from the inside out. First of all, where does the 2 go, or into which function does it go? Only into the g function. Now, if you plug a 2 into the g function, isn't that going to result in another number entirely? So you take that new number and plug that into the f function. You don't plug a 2 into both. 2 goes into g, so let's start with that. What is g of 2? G of 2, well, g is x plus 1, so if x is 2, that becomes 2 plus 1, which equals 3. So g of 2 is really equal to 3. So I'm going to replace the g of 2 with its actual value, which is 3. G of 2 is equal to 3. Now you find f of 3, which is 3 squared plus 2, 11. So on the test, you're going to have to find the composition of two functions at x, and you're going to have to find the composition of two functions at a value other than x. Is that clear on that? All right, here's a slightly more complicated composition function. Let's make this example 3. F of x equals 3 over x. G of x equals the square root of x plus 4. Okay. I want you to find f of g of x. So we're going to have this f of g of x means the g function is an input now inside of the f function. So what is g of x equal to? Square of x plus 4. So I'm going to change this into f. And instead of g of x in the parentheses, replace it with its function, or the equation of the function. So now I want you to find f of the square root of x plus 4. So now we have to consider the f function. The only spot in the function that anything could be placed as an input is this x in the denominator. So the f function says 3 divided by some kind of an input. Usually it's x, but x now gets replaced with what? Square root of x plus 4. Now, you may recall, it sounds like some of you recall, is it okay to have square root in the denominator? No. So you aren't going to want to leave it like this, but there's a simple fix. It's not a big deal. You multiply it by itself. You multiply this by the square root of x plus 4 over square root of x plus 4. So now in the numerator you have 3 times the square root of x plus 4 over, be careful here, Not quite, not quite. A square root times itself just gets rid of the square root and you're left with the expression inside. So it is x plus 4. So now, yeah, we have a little bit of a task before us, you guys. This is the composition right here, but what we don't have is the domain. Okay, this is a little more complicated than you might think. Not only do we have a denominator that restricts certain values of x, we also have a square root here that restricts even more values of x, because there are certain values of x that won't work not only as a denominator. For example, here's what I mean. Is it okay if I put a -8 right here for this x right there? Is that okay? Yeah, but is it okay if I put a -8 in there for that x? Is that okay? So -8 is not in the domain. So we have to decide what is and what is not in the domain. Let's first start with just the square root of x plus 4, and then we'll focus on the denominator. So what's the domain of the square root of x plus 4? We learned about this back in 2.1. You always take the expression inside of a square root, and what do you do with it? Greater than or equal to 0. Okay? Now if we were to solve that, you would subtract 4, and you say that x is greater than or equal to -4. So that's the domain of just this radical in the numerator. But look at what you've written here. You're saying that x can be greater than or equal to -4. But is it okay for x to equal -4? What would that do in the denominator? Make it 0. So we've got to modify this slightly. It's not x is greater than or equal to -4. What is it? X is just greater than -4. That takes care of the denominator and it takes care of the numerator. So the domain, I do not want you to leave it in this notation, though. This is not interval notation. If your x's start at -4 and go greater than that, what's the interval? Parenthesis.
0.
What? X could be 0.
It can't be 0 because 3 over x is one of your original functions.
Where were we?
0 plus 4 is 4. No, but the 3 over x, your f of x.
Then go to the first example.
Oh, I see. I see what you're talking about. I understand what you mean. This, once we form the composition, okay, this really isn't an x anymore. Do you understand that? Does that make sense? What you have to read originally here is this just means 3 over an input. And what does that input become? Square root of x plus 4. So now that gets replaced with, where did it go? With this right here. Does that make? I see what you're saying, but does that make sense though? So let's finish this up. Where do we go from -4, and it has to be a parenthesis. Why a parenthesis? Not equal to, and where do we end it? Where does it stop? Yeah. So I guess it actually doesn't stop. It goes from -4 till forever and ever. But that's the domain. That's 3.6. Combining functions. God. Yeah, 2.6. Did I call it 2.6 in the lesson? What did I call it? Oh, good, 2.6. Woo!